Good morning, students. Mr. Carver here. We're going to continue on with summation notation today, and we're going to apply it to area. All right, so let's start off with this function right here. F of x is equal to x squared plus 2. Let me sketch a graph of that. I'm exaggerating this drawing just slightly. In fact, let me redraw this. I don't like the way this looks. All right, that's slightly better. F of x plus 2, again, not to scale. I'm going to go, in this case, from 0 to 1. So when I talk about area beneath a curve, what I'm talking about is the area below the curve and above the x-axis within this interval. So really what I'm looking for is this area right there. Now, of course, this requires calculus, right? You've got a semi-trapezoidal area, but the top is curvy, so I can't use the trapezoid formula. And if you recall, the way we did it back in the day was we drew rectangles. All right, that might look a little familiar to you from the way back at the beginning of the year. That is chapter 1. Now, listen, you can use as many rectangles as you want. I'm going to use 5 rectangles just to kind of illustrate what we're doing here. All right, now if I label up the x-axis, and I'm going from 0 to 1 with 5 subdivisions, this first x value will be 1/5, 2/5, over to 3/5, 4/5, and then 5/5. And the reason I'm doing that is because the way we would come up with this estimate of the area underneath the curve is to find the area of each one of those rectangles, add those area figures all together, and of course we would come up then with an estimate that is not great, but it's certainly a ballpark estimate of the area underneath that curve. All right, so let's go ahead and do that now. And remember, what we're working from is this formula right here. Area is equal to width times height. So if I take the width of the first rectangle there, you can see that it is 1/5 wide. And then I'm going to write the height as a function of x. So in order to get this height right here, we'll do this in green. Remember, it's the right-hand side of each one of these rectangles that gives us the height. What I would do is I would plug in 1/5 into f of x, and again, that will give me this distance right there. So this is, in functional notation, that is written as f of 1/5. So essentially what I would do is I would square it, and then I would add 2 to it, and that would give me that green height right there. So that's the area of the first rectangle. The next one then is going to be also 1/5 wide. Each one of these is 1/5 wide. And the next height is then f of 2/5, because now I want to work my way across the x-axis. And now I'm looking for this distance right here, which is the height of the second rectangle. That's f of 2/5. Okay, the next one then is also 1/5 wide. And then the next is 3/5. And we just continue to work our way across, f of 4/5, all the way over to the last one, which is 1/5 wide, f of 5/5. Now, I'm not actually calculating the height of each one of these, but again, in order to do, like, say, the last one, you would take 1 or 5/5 and you would square it, add 2 to it, and that will give you this number right there. Then you'd multiply out the widths and heights, add all those numbers together, and you'd get a ballpark estimate of the area underneath the curve above the x-axis between 0 and 1. Now, we also talked back in the day about how to get a better estimate. And the way to get a better estimate of the area underneath the curve would be to use more rectangles. Thinner rectangles and more of them. So we might use 10 rectangles, 15, 20. The more and more rectangles you use, the less excess area you will have above the curve. And you can probably imagine what that would look like. Now, what we're going to do, at some point rather, if we move into, say, like 100 rectangles or 200 rectangles, it either becomes impractical or impossible to actually work through all of that. Actually, it never becomes impossible, just super, super tedious and impractical. So what we're going to do is we're going to let summation notation help us with this process. All right, now, what we want to do is I want to build in the formula for width times height, that is the formula for area, into my summation notation equation. And then I'll use the power of summation to add all of those together quickly, just like we did in part 1 of the 4.2 video. All right, so here we go. I'm going to start with I equals 1. I'm going to go all the way up now to some very, very large number. I want there to be hundreds of millions of rectangles because at some point, if I have an infinite number of rectangles going from 0 to 1, I'll have such little excess area above the top of the curve that my estimate will be so close to the actual area that it will cease to be an estimate. It will actually become the area underneath that curve. So I want to make n big. In fact, the way I'm going to do it is I'm just going to let that be n, and then just like we did before, I'm going to drive n to infinity. All right, so let's focus first on just the width of every single one of these rectangles. So stick with me here just for a second. If I go from 0 to 1 and I have 5 subdivisions, the width of every single one is 1/5. Let's say I had 50 rectangles. The width of every single one of those rectangles would be 1/50th. It would be a distance of 1 broken up into 50 equal subdivisions. Let's say I had 5,000 subdivisions, or 5,000 rectangles. Then the width of every single one would be 1/5,000th. I think it then stands to reason if I'm going to have n rectangles, that is hundreds of millions of rectangles, they are each going to be 1 over n wide. All right, that takes care of width. Let's talk about the height then. Now the height, again, is a function of my x as I work my way across from 0 over to 1 in this case. So check this out. If I had 5 subdivisions, I start with 1/5, I go to 2/5, then 3/5, then 4/5, and then 5/5. Let's say I have 1,000,000 subdivisions. I'm going to start with 1/1,000,000th and then 2/1,000,000ths, and I'm going to work my way all the way over to 1,000,000 1/1,000,000ths. All right, now if I have n subdivisions, I'm going to start with 1 over n, and then go to 2 over n, and then 3 over n, and I'm going to plug those into my f of x. So the way I'm going to write this is f of I over n. And if you recall from summation notation, remember I starts down here with this lower index, and then it goes all the way up to that upper number. And in this case, it's going to be hundreds of millions. So as I starts at 1, I will have f of 1 over n. Then I goes to 2, that's f of 2 over n. I go all the way up then to f of n over n, which is f of 1. All right, so now, once I figure out what this is, I will actually have the area underneath that curve from 0 to 1. So let's work on that green box right there. Let's do this on the next page then. All right, so now I've got that summation there, 1 over n, f of I over n. Now, remember that f of x is equal to x squared plus 2. And in order to find the heights, what I do is I take that x, or whatever number is inside here, and I plug it in for my x in f. So that's what I'm going to do now, because I can't really evaluate f of I over n. I don't have anything to work with. So again, what I'm going to do is I'm going to take I over n, and I'm going to plug it into f of x. This is then going to give me, all right, and this is what I'm going to get. I take the limit then as n goes to infinity. Got the sum from I over 1, I equals 1 rather to n. I've got 1 over n. And again, what I'm going to do is I'm going to take I over n and plug it into f of x. This gives me I over n, the quantity squared, plus 2. And 1 over n is being multiplied by that entire thing. Now again, remember, for summation notation, you cannot have quantities raised to a power, you can't have products, and you cannot have quotients. So I'm going to start simplifying this, just like I did in the part 1 video. Take the limit, as n goes to infinity, sum from I equals 1 to n. I've got 1 over n. What I'm going to do is square that in there. That's I squared over n squared plus 2. And now what I want to do is distribute 1 over n to both of those. This gives me now, again, the limit as n goes to infinity, I equals 1 to n. This is going to be I squared over n cubed plus 2 over n. And just like I did in the part 1 video, now I'm going to split that into 2 different summations. Still, of course, taking the limit as n goes to infinity. I have the sum from I equals 1 to n of I squared over n cubed plus the sum from I equals 1 to n of 2 over n. Also, just like in part 1, I'm going to pull through the summation, everything except for except for that which I have a formula for. So the next line, let me clean this up here just a little bit, get this out of the way. The next line then will be the limit as n goes to infinity of 1 over n cubed times the sum of I squared. The next will be 1 over n times the sum of I equals 1 to n of 2. This is, by the way, also I equals 1 to n. And now what I want to do is pull out these two summations and replace them with what I have a formula for. This will then, of course, still be the limit of 1 over n cubed. N squared is n plus 1, 2n plus 1, all over 6. This is going to be plus 1 over n times 2n. Now again, what I want to do is take the limit as n goes to infinity. So what I'm looking for is the most dominant term in the top and the bottom of each one of these. And again, just like we did in part 1, if I FOIL out the top of this first one here, I'm going to get 2n cubed over 6n cubed. By the way, I have lots more stuff on the top, but it is all, none of it is as powerful as 2n cubed, excuse me. The next one is going to be then 2n over n, and I'm taking the limit as n goes to infinity. Well, what happens is you've got equally powerful terms in the top and the bottom. You just take the coefficients out in front, so that turns out to be 1/3. Those n's cancel, and that's going to be 2. My answer is 2 and 1/3. Now, this is the sum of an infinite number of rectangles going from 0 to 1, which to me is absolutely fascinating. Look, we just added together an infinite number of rectangle of area numbers, basically, from 0 to 1, and we got 2 1/3, and we did it in about, what, 2.5 minutes. Fascinating. All right, let's look at a more difficult problem, maybe where we don't just have a distance of 1 going from 0 to 1. Let's change that interval. All right, let's use the same curve. Let's do x squared plus 2, but now I'm going to go from 1 to 3. All right, so if I draw a quick picture, x squared plus 1, but now I'm going to go from 1 over here to 3. All right, now in the previous example, I had a distance of 1 broken up into an infinite number of subdivisions. Now I have a distance of 2, right? I'm going from 1 to 3. All right, now again, what we're going to do is we're going to work off of this formula here. Area is equal to width times height, and I want to build that into my summation. So I'm going to go from 1 to n, eventually driving n to infinity. Let's start off with width. In the previous example, I had a distance of 1 broken up into n subdivisions, so the width of every one was 1 over n. Now I have a distance of 2 broken up into n subdivisions, so I think it would make sense that the width of every one will be 2 over n. Now, the height. Remember, the height of the first rectangle is going to be just to the right of 1 there. Not to scale, so it looks something like this. So I want to know what that is right there. That is going to be just to the right of 1. In fact, if the width is 2 1/billionths, essentially, right, as n gets really, really large, 2 1/billionths, this first question mark here, the width, the first x value that I plug into x squared plus 2 will be 1 and 2 1/billionths. But I need to be to the right of 1. So here's how you write that. That's f of 1 plus 2 1/billionths. Right? It's just to the right of 1. It is 2 1/billionths to the right of 1. Now, the next one here will be 2 and 4 1/billionths. The next will be 2 and 6 1/billionths. And the way to get this 2 to go from 2 to 4 to 6 to 8 is to multiply it by I. All right. Because when I is 1, it's f of 1 and 2 1/billionths. When I is 2, it's f of 1 plus 4 1/billionths, etc. All right, now there is a shortcut here, in case you're completely confused as to what I'm talking about. And by the way, now we've crossed off the height as well, so we've got what we need. How about this? That's always distance over n. And when I say distance, I'm talking about the distance from left hand to right hand. This is always the left bound. And that's always distance over n times I, every single time. So, for instance, let's get rid of all this stuff. Let's say that I'm using the same curve, and instead of going from 1 to 3, now I'm going to go from, let's do 3 to 9. Well, the way I would build my summation notation is, according to what I just had written down, it's going to be distance over n, right? 3 to 9 is 6. And then f of left-hand endpoint plus distance over n I. So there's a shortcut you can use from here on out. Distance over n, f of left-hand endpoint plus distance over n I. All right, so let me go show you, and from here on out, it's basically what we've already done before. What I want to do now is, this is the hard part to remember, I want to take this, and I want to plug it into my x in f. So this turns out to be the sum of 2 over n, and this is going to be 1 plus 2 over ni, the quantity squared, plus 2. And it's 2 over n times that entire quantity. Now I just want to clean this up. First, I'll FOIL this out. This is the sum of 2 over n. This is 1 plus 4 over ni plus 4 over n squared I squared plus 2. Now, if it's hard to see where this answer is coming from, you can take this portion right here and square it using the box or using the FOIL method. All right, so let's continue to clean up in here. The 1 and the 2 combines to give me 3 there, and then I'll distribute this over all 3. So this gives me the sum of, that looks like 6 over n plus 8 over n squared I plus 8 over n cubed I squared. And now what I want to do is break all of them up. And while I'm at it, I'm going to pull through all the constants. So this turns out to be 1 over n times the sum of 6 plus 1 over n squared, 8 over n squared times the sum of I, plus 8 over n cubed times the sum of I squared. So I'm applying summations to every single one of them and then pulling through the summation constants. That is constants or n. N is really a constant, right? By the way, all of these are going from I equals 1 to n. Just not writing that on every single one. So now what I want to do is I want to take out each one of these, and I want to replace it with their formulas. Make a little bit more room here. All right, so here's what I've got. I have, the first one is 1 over n times 6n, because 6 is just a constant. The next is 8 over n squared, and then I have the sum of I, which is n times n plus 1 all over 2. The last one is 8 over n cubed times n plus 1, 2n plus 1, all over 6. And again, what I'm going to do now is I'm going to take the limit as n goes to infinity. So I'm looking now for the most dominant terms in the tops and the bottom. So this gives me 6n over n for the first one. The next one is going to be 8n squared plus other stuff that I don't need, all over 2n squared. The next one is going to be 16n cubed plus a bunch of other less powerful stuff, over 6n cubed. And again, because I'm taking the limit as n goes to infinity, I don't need the lower powered terms of n. So again, if I've got equally powerful tops and bottoms, I just take the coefficients out in front. So this first one will go to 6. The next one goes to 4. The last one goes to 16/6 or 8/3. So it looks like this is 10 plus 8/3. I get a common denominator. That is 30 plus 8 over 3. This gives me 38/3. And again, what we just did was we multiplied base times height of an infinite number of rectangles going from 1 to 3 underneath x squared plus 2 in just a matter of minutes. And we came up with a super, super, super exact estimate, really not even an estimate of the actual area underneath the curve. It's fascinating. All right, people, that should be enough to get you through today. Thanks for hanging in very much. See you soon.